Okay, let's go over the rules of assigning oxidation numbers. Rule number 1, the easiest out of them all. Uncombined elements have oxidation number of 0, which means that whenever we see an uncombined element, sodium, sulfur, phosphorus, oxygen, fluorine, their oxidation number would always be 0. Rule number 2. For elements when they are combined with other elements, the oxidation numbers are equal to ionic charge, which is great because we know a lot about ionic charge. For example, we know that elements from group number 1, when they become ions, they would always have charge +1. And the elements from group number 2, when they become ions, they would always have charge +2. The elements from group 17, also very predictable. Whenever they are ions, they have charge -1. Charge of transitional metals, metalloids, and nonmetals, other nonmetals, but the nonmetals from group 17, they are a little bit tricky. They can change. However, we can always rely on oxygen to be -2. There are very rare cases of exception when oxygen is -1, it's in peroxides. In this case, oxygen is -1 and hydrogen is +1. But these cases are very rare. Usually, whenever you see oxygen in the combination with other element, the charge of the oxygen would be -2. And we also can say something about hydrogen. Hydrogen will almost always, whenever it's in combination with other elements, almost always has the charge +1. Unless it's a very rare case when hydrogen is standing next to a metal like lithium. In this case, rare case, hydrogen would carry charge -1 and lithium would be +1. Rule number 3. The sum of oxidation numbers in all compounds must be 0, which is understandable because we remember that the compounds must be electronically neutral. So let's look at the example. Here's sodium chloride. And we know that chlorine belongs to group number 17, so the charge, ionic charge, is predictable, it's -1. And sodium belongs to the group number 1, so the charge is predictable, +1. And we can see that the sum of these oxidation numbers would give us 0. Perfect. Let's look at a different example. Sulfur dioxide. And the oxidation number of sulfur can be tricky. It can vary. But we have here in this compound oxygen. Oxygen is almost always -2, so that would help us to figure out the oxidation number of sulfur. Considering that we have 2 oxygens and each carries -2 oxidation number, so the oxidation number of sulfur, to balance out the 2 of -2's, we have to have +4. Let's look at a different example. H2S, another compound with sulfur. Let's see what's going on with the oxidation number on this sulfur. Once again, sulfur can have different oxidation numbers, but we have hydrogen here, and hydrogen is practically always +1. Then, to balance out 2 hydrogens with the oxidation number of +1, we need to put the oxidation number of sulfur -2. Let's look at the example of carbon monoxide and carbon dioxide. Well, in both cases we have oxygen in the compound, and the charge on oxygen is always minus 2 over here. To balance out this oxidation number, the oxidation number of carbon must be plus 2, and in this compound the oxidation of the carbon must be plus 4 to balance out 2 of the minus 2 oxidation numbers on the oxygen. The last rule. The sum of oxidation numbers in the polyatomic ions must be equal to the charge on the ion. Let's see on the example what it means. Let's say we have SO4 2- ion. This is sulfate ion, and the overall charge on the entire ion structure is minus 2. So let's try to find out what oxidation numbers are on the species within this ion. We have oxygen, which is predictably minus 2. And we need to balance the oxidation number of the sulfur in a way so together the oxidation number of sulfur and oxidation number of on the oxygen together they would give minus 2. So plus 6 seems to be like a great decision, because we have plus 6 on sulfur plus minus 8 that we have on the oxygen. Together it's minus 2. Or let's look at the hydroxide ion. The charge of hydroxide ion is minus 1. This is the charge that carries the entire structure of the hydroxide ion. Now, our task is to figure out oxidation numbers on the species within this ion. And we have hydrogen here, which is beautiful because we always know the charge of the hydrogen. It's almost always plus 1. And the charge, the oxidation number of the oxygen is also predictable. It's almost always minus 2. So we have minus 2 plus 1 on the hydrogen, and together it gives us minus 1, which is what we wanted. Let's assign oxidation numbers to the elements within these two reactions. So we have cobalt and lead standing here all by themselves. They are uncombined elements, so their oxidation number is 0. And we have Cl ions, chlorine ions, and their charge is predictable. It's minus 1 and minus 1. So to balance out the minus 2 that is here on the two chlorines taken together, we have to assign oxidation number plus 2 for the cobalt and plus 2 for this lead. And you can see that here the cobalt was 0 oxidation number and it became plus 2. And lead that used to have the oxidation number plus 2 eventually has the oxidation number 0. Now let's work with this reaction, the reaction of neutralization, as you can see. Because we have acid reacting with base, producing salt and water. But let's concentrate on oxidation numbers. So we have hydrogen, which is always plus 1. We have oxygen, which is always minus 2. And considering that the entire compound has to have neutral charge, the charge of 0, so the sulfur is supposed to be plus 6. So we have plus 2 from hydrogen, we have plus 6 from sulfur, and we have minus 8 from the oxygen, which makes it 0. Perfect. Let's continue. This hydrogen with this within this hydroxide ion would have a charge, of course, plus 1, the oxygen minus 2, and calcium belongs to the group number 2, so the charge is once again predictable, plus 2. And on the product side we have oxygen, which is always minus 2, as well as here the hydrogen would always be plus 1, and calcium plus 2 because it belongs to the group number 2, and sulfur over here will be plus 6. And here's the great point that I want to make. I want you to understand that not all reactions are redox reaction. This one can be classified as redox reaction because we can see the change in the oxidation number. The cobalt used to have oxidation number 0, and over here it has oxidation number plus 2, so it lost electrons. The lead that used to have charge plus 2 gained those 2 electrons and became the lead with the oxidation number 0. Over here in this reaction, we don't see, if you compare all the charges on the reactant side and on the product side, you will see that none of the species changed their charge. So this reaction is not the redox reaction. Go over the rules of assigning oxidation numbers on your own, because you should be able to assign oxidation numbers to compounds and polyatomic ions.